Okay, let us continue from where we stopped. The second characteristics of a DC generator is internal or total characteristics of DC generator. We have seen the open circuit characteristics of our DC generators, and the next is the internal one. So this total characteristic curve, it tells you the relation between no load voltage, no load generated voltage EG, and the armature current I, considering the effect of armature reaction. Considering the effect of armature reaction. We'll come to it later on armature reaction. Just to give you some hint about armature reaction. This armature reaction is a reaction, it's almost against the reaction which is happened in almost all DC machines, and its effect is it reduces the generated voltage. It also creates cross magnetization effect inside the machine that totally leads on the decrement of the performance of our DC machine, what we call that armature reaction. So by considering that effect, if we try to plot the curve, the generated no load, on load EMF or generated voltage while loading and the armature current, if you try to plot EG versus IA, it gives you the internal or total characteristics. Why we need to know significance of knowing this curve is the internal characteristics give you better idea of our actual EMF generated in the armature winding after counting for the demagnetization effect of the armature reaction. So by considering the armature reaction, how much the voltages can be generated from our generator is going to be known from this total characteristic curve. From this total characteristics. So in a normal generator, as you remember where we are talking last time, generating the equations, we know that on load generated EMF is always less than no load generated EMF due to the armature reaction. It means, just to show you, normally our EG, our generated voltage, internal generated voltage is going to be no load voltage minus armature reaction. So in another term, our no load voltage is going to be internal generated voltage plus armature reaction. This reaction is a reaction which is having an effect on the performance of our DC generator. Effect means it will directly reduce the generated voltage. So we can say our generated voltage, internally generated voltage, is less than our generated voltage less than no load voltage. That's what this term is saying. So on load voltage EMF, while loading our DC machine, if we try to measure the voltage internal generated, it's always less than no load voltage. Why? Because here it is mentioned that the internal generated voltage during loading is determined by subtracting the voltage drop here. See, subtracting the voltage drop due to the magnetization effect of the armature reaction from no load voltage. Therefore, this curve definitely lies below open circuit characteristics curve. It lies below that. See, this is a no load voltage. So if you see this curve, we call it as a no load voltage curve. It is a no load voltage curve. So if we subtract the effect of this armature reaction armature reaction, it will give you this internal characteristic curve. Because like we have seen in our previous one, we said that internal generated voltage is going to be no load voltage plus internal generated voltage is going to be no load voltage minus armature reaction. So AB, now in our curve, this AB is no load voltage, E naught, right? E naught. If you subtract armature reaction from that, we'll get this internal generated voltage. What do you call it? EG, internal generated voltage. Internal generated voltage. So if you consider a separately excited DC generator giving its no load voltage E naught for a constant field current, if there is no armature reaction, obviously if this armature reaction is not there, E naught, EG is equivalent to E naught if it is not there. But if there is armature reaction, E naught minus armature reaction will give you EG, which is internally generated voltage. This is an internal characteristic curve of our DC generator. So we can simply say internal characteristics can be obtained from no load open circuit characteristic curve minus armature reaction. From E naught, if you subtract armature reaction, we'll get internal or total characteristic. This curve cannot be obtained directly by experiment. We cannot get it because our voltmeter cannot measure that very small magnitude of voltage generated internally. Due to this, the voltage drop in the armature resistance will take that smaller voltage level. See, we said VT is going to be generated minus IARA. So if this is very small, and also if we have ohmic drop, what we call it armature, ohmic drop, IARA, then this is going to be very small, very difficult to measure it. Okay, very difficult to measure it. So that cannot be experimentally found, but by using galvanometer, we may detect some amount. So the internal characteristic can be determined from external. Once we know that, if we are able to know the external characteristics, which we are going to cover it on the next. If we know that, we can get the internal characteristics. That simply means that the external characteristics, just see for this curve, this is external characteristic curve. So external characteristics is simply internal characteristic minus ohmic voltage drop. Ohmic voltage. What is ohmic voltage drop? This one. This is an ohmic voltage drop inside the armature. So if we subtract them, we can know internal current. So external characteristics plus ohmic voltage will give you internal characteristics. Have you understood? Now, just to repeat this point, internal characteristics can be known in two ways. One, by knowing the open circuit characteristics, if we subtract armature reaction drop from open circuit characteristics, we can get the internal characteristics. Second, if we are able to know the external characteristics plus ohmic voltage drop, IARA, will give you internal characteristics. That is a thing what I want to say here. And the third, external characteristics or load characteristics. These characteristics tells you the relation between terminal voltage and load current in a DC machines under loading condition. So obviously, terminal voltage is always less than generated voltage. Here we say terminal is going to be EG minus VT. So always VT is less than, VT is less than EG. This is always true. Due to the voltage drop in the armature circuit. Therefore, this curve will lie below. Obviously, it lies below internal characteristics. As the load increases, now this characteristics is evaluated under loading condition. I say, as the load increases, the terminal voltage falls or decreases due to two reasons, obviously. Now, say, V terminal is going to be EG minus IRA, we say. So, as the load increase, as the load increase, it says terminal voltage get decrease always. Why? One, the armature reaction weakens the main flux so that actual EMF generated on the load is less than the generated no load condition, on load condition. It says, due to the armature effect, one of the effects of the armature, we said that it demagnetizes the flux inside the machine. If the demagnetization is happening, generated voltage will going to be reduced, because we said that EG is K phi N. So demagnetizing reduces this flux. If flux reduced, EG get reduced. If EG get reduced, definitely terminal voltage will get reduced. That is one reason. Second reason, there is a voltage drop across armature resistance. It means as the load increase, IA will get increase, obviously. If IA get increase, EG minus this maximum increment will get reduced this VT. So it will reduce. Due to this external or load characteristic curve is below the internal characteristic curve, because now two effects are coming into picture in this case. One, armature reaction effect is there, it is reducing VT. Second, ohmic loss IARA is there, again they are also reducing. So the curve is definitely below the internal characteristics. That's why it is coming below this internal characteristics. Why we need to know this external characteristics curve? This curve is critical for understanding the voltage regulation of our DC machine as the load varies. Obviously, generators are quality of generator are going to be evaluated with their voltage regulation. Voltage regulation means voltage of the generator at no load minus voltage of the generator at full load divided by voltage of the generator at full load times 100. So this regulation is going to tell you the quality of our generator. So this quality of the generator will come from this curve called external curve. It helps the machine, or it helps determining how the machine will perform when connected to an external circuit, how it is performing at different loading conditions. That behavior of our machine is going to be determined from this external characteristic curve or load characteristics curve. This curve can be obtained by making the following circuit connection. If you have variable DC supply, and if you connect the variable DC supply to our field winding, and we have to connect ammeter here to measure the current, and we have to connect our armature with voltage and the ammeter. So simultaneous measurement of voltage and the load current, measuring this voltage and the current simultaneously, and if we try to plot I load versus V, friend, I load versus V terminal, this V versus I, it means it gives you external characteristics of our DC generator. That's it about the characteristic curve or the behavior of our generator with different loading condition. So the next point is control of terminal voltage. How we can control the terminal of our DC generator. This, in order to know how the method to control, we have to remember the equations, EMF equation for our DC generator, particularly here, separately excited DC generator. From the equations, Vt Ia or Ig minus IARA, the terminal voltage of a separately excited DC generator can be controlled by changing the internal generator voltage of the machine. What does this mean? We can control, just from the equation itself, we can know the methods of controlling terminal voltage of our generator. It says Vt Eg minus Ia Ra. So our intention is to control this. How we can control this? We can control this either by controlling this or by controlling this. Just two methods we can use. One method by controlling internal generated voltage. The second method by controlling this drop. So, how we can control this? How we can control the internal generated voltage? One, changing the speed of the rotation we can control. What does it mean? Now this Eg means, we said it is K phi n, right? So, in order to control Eg, this Eg, I can control this n or I can control this flux, right? Machine constant is already finished manufacture. So, these two methods we can control Eg by these two methods. So, how we can control that? Changing the speed of the rotation is one way of controlling. By the way, don't confuse this formula with rad per second revolution per minute. This means we can say K phi omega. I hope you remember this. So by controlling this speed of rotation, we can control this. If we are able to control this, we are able to control terminal voltage. Second method of controlling the terminal voltage, changing the field current. If IF is decreasing, then the field current increases. Therefore, the flux phi in the machine increases. As the flux rises, E generated will rise, must rise too, so Vt will get rise. So it means by controlling this, we can control this. If we are able to control this, we are able to control E also. How we can control the flux is the question. Flux, how we can control? By controlling IF. How we can control IF? IF is going to be controlled by controlling VF by RF. So by controlling or making this RF variable, we can control this variable. If we made able to make this IF variable, we can change flux. If we're able to change the flux, sorry, let me write it again. And IF is going to be VF and RF. So by varying this, we can vary this. If we are able to vary this, we are able to vary flux, right? If flux is changed, we are able to change or vary our EG. If this varies, this is going to vary. If EG is varied, we are able to vary our terminal voltage of our generator array. This variable means is also variable. That is a way. So there are two methods of controlling the terminal of our separately excited DC generator. What are they? One, changing the speed of the rotation or controlling the rotation of the DC generator. It will change the terminal voltage. Second, changing the field current. Then it will change the terminal voltage of our generator. In many applications, the speed range of our DC generator is controlled by prime mover, we say. So we cannot vary the prime mover speed with a large variation, only quite limited variation can be possible. Therefore, terminal voltage is mostly controlled by changing the field current. Is a common one, common practical applicable terminal voltage control in separately excited DC generator is by changing the field current. How we can change the field current? By applying a variable field resistor, we can control the current will control the flux will control the internal generated voltage, it control terminal voltage of our DC generator. Finally, on the separately excited DC generator, we'll see application. Where are we going to use such type of generators? This type of DC generator are generally more expensive than self-excited DC generator. Why? Because it needs additional DC power supply. Additional DC power supply is required. Because of then its cost is going to be separately excited generator plus one DC supply cost. So because of that, their applications are restricted. They are generally used where the use of self-excited generator are unsatisfactory. If we need for some application our generator, and fortunately if that generator is self-excited and we are not able to get satisfactory operation, especially in controlling the characteristics, we may force to use such type of generators. And because of their ability of giving wide range of voltage output, they are generally used for testing purpose in laboratory. See, in a separately excited DC generator, since the field winding supply and armature terminal voltage are different, it gives you an opportunity to vary the output voltage because they are totally independent. So due to this, it will allow you a wide range of output voltage than a self-excited system. So this behavior of the DC generator will make it selectable for testing purpose in laboratories. It allows you the different output voltage to be generated. And lastly, a separately excited generator operates in a stable condition with any variation in field excitation. Why? Because they are totally separated. The field and the armature are separated. So because of these properties, they are used as supply source of DC motor. They are used for driving of DC motor, whose speeds are to be controlled for various applications. That is quite a specific application of such type of DC generators. So that's what I have on a separately excited DC generator. So on next class, we're going to continue our discussion on shunt DC generators. So as I told you last time, please you try to attempt different equations related to separately excited DC generator from the references given to you. And if you have any questions, suggestions, please, you're welcome. I'm ready to clarify your doubts. Thank you.